Hi folks, we're going to take a look at this first question on the related rates sheet. So let's take a look at the question. It says a balloon rising straight up is tracked by a finder 500 meters away from the liftoff point. So right away I'm actually going to start drawing my picture right away. So here, this will be the ground, and here I've got my rangefinder, and 500 meters away we have a balloon going straight up into the air. Okay, so this is 500 meters away. Okay, and it says at the moment that the angle of elevation of the balloon from the rangefinder, so we're going to be working with the angle of elevation from the rangefinder, the angle is increasing at 0.4 radians per minute. How fast is the balloon rising at that moment? Okay, now you notice here I'm not going to put the pi over 4 in my drawing yet because this is something that's a changing quantity, as is the height. Okay, I'm looking for the rate of change of the height at that particular moment, but as I'm setting up my problem, I want to avoid putting any numbers on here that are not fixed. I put in the 500 meters because this is a fixed quantity. Okay, the distance from the rangefinder to the launch point always remains 500 meters. But since they're giving me information about the angle, I'll set that variable into my diagram. And they're looking for information about the height. I'm going to set that variable into my diagram. So remember how related rates work. Is we're trying to determine the rate of change of the height of the balloon, and we're given information about the rate of change of the angle of elevation. Okay, so if we can find a relationship between these variables, we can use that to find the relationship between their rates of change. So you look at this diagram here, and I think it's pretty clear that the relationship that we're going to use is going to be the tangent ratio, because the tangent of this angle is the height, which is what we're looking for, over the over this adjacent side, which is the fixed 500 meters that we know. Okay, so the relationship we start with will be tan theta equals h over 500. Okay, now what we're looking for is the rate of change with respect to time. Okay, we don't have a function here that's explicitly given with respect to time, but we're going to use implicit differentiation to do that. So here I'm going to take the derivative with respect to time of both sides of the equation. Okay, and so here I'm going to have to use the chain rule, because here I'm going to take, so here you have tan theta is a function of theta, and theta itself is a function of time. Okay, so what we can do is use a chain rule, and first I'm going to take the derivative of tan theta with respect to theta, and then multiply that by the derivative of theta with respect to t. Okay, so this is just an application of the chain rule on this function with respect to time. Okay, and same thing on the other side of the equation. First, I'm going to take the derivative of h over 500 with respect to h, and then multiply that by the derivative of the height with respect to time. So again, another application of the chain rule. Okay, often I wouldn't write this equation down, or that step down, because we've done implicit differentiation and the chain rule quite frequently at this point. So derivative tan theta with respect to theta is secant squared theta, okay, and d theta dt, okay, stays there. Here, take the derivative here. The 1 over 500 is just a constant, okay, and then of course the derivative of h with respect to h is just 1, and then I'm just left with dh dt. Okay, and what I'm going to do now is I'm going to input the information that I know. So we notice that this relationship between the rates of change has a secant squared theta in it. So that's why they needed to give us a specific moment in time. They could only determine this rate of change knowing a particular angle. Okay, so it kind of makes sense because the relationship between h and theta is not a constant relationship. Okay, so here they give me the specific angle they're interested in. So here this will be secant squared of pi over 4. Okay, d theta dt is a given quantity. We know how the angle is changing with respect to time. So times 0.14. Okay, and then here 1 over 500, and dh dt is what we're looking for. So that remains our unknown. Okay, so we had enough information given that we're able to solve for dHdt, which is what we're looking for. So dHdt is equal to, and let's calculate that here. Okay. Now, really, secant squared of pi over 4 I should be able to do in my head. Okay, so pi over 4, 1 root 2. So secant is 1 over cosine. So cosine is 1 over root 2. So this will just be root 2 over 1. Okay. So I know that secant squared of pi over 4 will just be root 2 squared. Okay, which is just 2. But of course, calculator will do the work for you if you don't want to go through that process. Okay, times 0.14 equals, and now of course we're going to bring the 500 to the other side, so times 500, and we have 140. Okay, and our units here, well, the distance units are given in meters, so this is meters, and the time units are given in minutes, so meters per minute. Okay, so that's it for this one here. So just to recap, okay, the diagram is essential here because we want to make sure we're using the relationship that actually connects the variables for which we have information or which we're actually looking for. In this case, here's the tangent ratio. Okay, I differentiate both sides with respect to t. I apply the chain rule when needed, and then from there, see that I have enough information given in the question to be able to input everything other than the quantity that I'm looking for. Okay, that's it for now.